Astronomers have documented 9 peculiar aspects of the object designated 3 Atlas, but the 10th anomaly presents a distinct challenge, unsettling even the most seasoned scientists. This celestial visitor, detected traversing our solar system, exhibited an inexplicable surge in speed and a deviation in its trajectory while in proximity to the Sun. This acceleration was not a consequence of gravitational pull nor gas expulsion, but rather an unknown impetus. All prevailing models predict that such a maneuver necessitates a dramatic energetic event, resulting in a massive expulsion of material and the formation of a debris cloud, potentially surpassing the height of Mount Everest and comprising billions of tons of dust and vapor ejected into space. However, telescopic observations revealed no such spectacle. There was no visible plume, no discernible fragments, only an object continuing its silent, accelerated motion. If subsequent observations conducted between November and December of the year 2025 continue to find no trace of this hypothesized debris, then 3I Atlas will have achieved something unprecedented for any known comet. It will have altered its course through space without expending any observable mass. This suggests a force without an apparent origin, a motion seemingly born from nothingness. Join me until the conclusion as we delve deeply into this 10th anomaly, the one that has, surprisingly, been overlooked. For if it possesses the capability to alter its trajectory once, what prevents it from doing so again, perhaps steering its path toward Earth? If this enigma captivates you as it does me, do not merely observe from the periphery. Engage in the pursuit. Click the like button and subscribe to Cosmo Chill to ensure you don't miss any subsequent developments as this narrative continues to unfold in real time. Please share your viewing location, the current time there, and your thoughts on this 10th anomaly. To support the growth of this community, consider sharing this video on platforms such as X, Facebook, Reddit, or even within your personal group chats. Your engagement is the driving force that enables us to continue investigating stories of this nature. Therefore, we extend our sincere gratitude for your unwavering support. Part 1. The Revelation. Envision an entity originating from an entirely different stellar system, hurtling through our solar neighborhood at velocities that render a projectile seemingly stationary. Furthermore, imagine this object performing a feat that no known comet is capable of. You might be inclined to dismiss this as another peculiar space rock or an exaggerated claim designed for clicks. However, the distinction of this phenomenon lies in its fundamental difference. The very reason for its peculiarity is a concept that, upon proper contemplation, is likely to induce sleepless nights. This celestial body bears an identifier that sounds remarkably like a password reset code, 3I Atlas. For clarity, it is referred to as 3I Atlas, where the I signifies its interstellar origin, marking it as the third confirmed visitor from beyond the confines of our solar system. The initial visitor, Oumuamua, sparked considerable debate among scientists regarding its classification as a comet, asteroid, or something entirely alien. Following Oumuamua was Borisov, which behaved precisely as a conventional comet, offering a sense of reassurance that our understanding of the universe remained intact. And then 3 Atlas arrived, prompting the universe to declare, "Not so fast. Here is what you must grasp immediately before we proceed further." This object exhibits 9 verified anomalies, 9 distinct instances where it defies established rules, manipulates probability, and compels astronomers to re-examine their calculations and verify their findings. We will briefly touch upon these in a moment, but first, I implore you to focus your attention on the aspect that is currently not being widely discussed, the 10th anomaly. the one that elevates this discovery from merely extremely peculiar to a situation that may necessitate a complete reassessment of our understanding of celestial object dynamics. The 10th anomaly is this. 3I Atlas appears to have undergone a non-gravitational acceleration in the vicinity of its perihelion, the point of its closest approach to the Sun. To reiterate, this object altered its speed and direction in a manner that cannot be attributed solely to gravitational influence. Comets commonly exhibit such behavior. They heat up, release gases, shed material, and experience a propulsive effect from the expulsion of ice and dust. This is considered a normal and expected phenomenon. However, the predicament arises here. If 3I Atlas accelerated as indicated by the measurements, it should have expelled a quantity of material exceeding 5 billion tons. 5 billion tons. This is not an error in transcription. When a comet ejects 5 billion tons of ice, dust, and rock, the effects are observable. A vast luminous debris cloud becomes apparent. Tails extend across the celestial expanse. Brightness surges are recorded. Evidence is abundant. Yet, thus far, no such evidence has been observed. Not at the magnitude anticipated. This leaves two potential realities, and I must confess, neither is particularly comforting. Either we are somehow failing to detect the debris cloud, in which case this is an exceptionally unusual but fundamentally natural comet, or the object accelerated without expelling the expected mass. If the latter scenario is indeed occurring, then we are confronting something that fundamentally contradicts our established principles of momentum and mass. It is an entity that alters its direction without expelling material in the opposing direction, an object that moves with what appears to be intent. Before you conclude that I have veered into speculation, allow me to guide you through the 9 anomalies that are already established. These are not theoretical postulations. They are derived from measurements, observations, and peer-reviewed data, collectively representing a series of remarkable peculiarities. Firstly, its trajectory. The object entered our solar system on a retrograde orbit, meaning its motion is counter to the direction of most celestial bodies within our solar system. However, its path demonstrates an unusually close alignment with the ecliptic plane. The probability of such an alignment occurring by chance is approximately 0.2%. While not impossible, this is an uncomfortably low probability. Secondly, the timing. It passed in proximity to Mars, then Venus, and subsequently Jupiter, all within a highly improbable temporal window. Some estimates suggest the probability of such an alignment, assuming a purely random path, is less than 0.005%. Again, this is not an impossibility. However, when a series of low-probability events are accumulated, one begins to question whether one is witnessing a coin toss or a conjuring act. Thirdly, its size and velocity. This object is both larger and faster than previously observed interstellar visitors. Oumuamua was small and exhibited tumbling motion, disappearing before it could be thoroughly studied. Borisov was of moderate size and behaved conventionally. 3I Atlas, however, is neither small nor conventionally behaved. It moves with a discernible purpose, or at least with a momentum that suggests an exceedingly prolonged journey. Fourthly, its composition. The ratios of constituent gases deviate significantly from expectations. Specifically, the nickel-to-iron ratio and the nickel-to-cyanide ratio are anomalous. These figures do not align with those observed in comets originating from our solar system. They represent extreme outliers, even among unusual cases. Fifthly, its water content. Most comets are essentially frozen aggregates of ice and dust, predominantly composed of water ice. 3I Atlas contains approximately 4% water by mass. 4%. This is not characteristic of a dirty snowball. It suggests a composition derived from entirely different formative conditions, distinct from those understood within our solar system. Sixthly, the polarization. The manner in which light reflects off this object is unprecedented. It exhibits extreme negative polarization, a minimum of approximately -2.7% at a phase angle of 7 degrees. While this may sound technical, its implication is profound. The surface or the particles surrounding this object reflect light in a way that is uncharacteristic of any known comet, presenting a unique polar signature absent from our comprehensive database. Seventhly, its brightness and color. As it approached the Sun, 3I Atlas intensified in brightness at a rate exceeding that of any known comet. Furthermore, its color shifted towards blue. Typically, comets appear redder as they heat up due to the prevalence of dust influencing reflected light. This object, conversely, turned bluer than the Sun itself, a phenomenon that contradicts established expectations. Eighthly, the anti-tail. Comets typically exhibit tails that extend away from the Sun, propelled by solar wind and radiation. 3I Atlas, however, produced a sun-facing jet, an anti-tail. While this can occasionally be an optical illusion caused by the viewing angle, the observations suggest its authenticity. Material was being expelled in the direction of the Sun, or at least in a direction that defies conventional cometary physics. And ninthly, its origin. The object originated from a celestial direction nearly identical to that of the renowned WOW signal detected in 1977 within approximately 9 degrees. The WOW signal, for those unfamiliar, was a powerful, narrow-band radio transmission detected by a SETI telescope, which was never repeated, never explained, and emanated from a specific region of the sky from which 3I Atlas subsequently appeared. The probability of such a coincidence is, to put it mildly, suggestively improbable. Therefore, these are the 9 distinct reasons why this object should not manifest in its observed characteristics, 9 ways it defies our expectations, our models, and our perception of normalcy. And then there is the 10th anomaly, the acceleration without discernible debris, the propulsion without observable exhaust, the alteration of motion without the requisite reaction mass to account for it. This is the anomaly that unifies the others and renders them profoundly unsettling. Because herein lies the crux of the matter. If our current understanding is flawed, if the debris cloud is indeed present but simply undetected, then 3I Atlas serves as a humbling reminder that the universe is more complex than we imagined, yet still governed by discernible laws. However, if our assessment is correct, and if the follow-up observations in November and December of 2025 fail to reveal the debris cloud, then we must confront a far more disquieting possibility. Either our fundamental physics is incomplete, or something external possesses knowledge beyond our current comprehension. Over the next hour, we will meticulously dissect this phenomenon, examining the observations, the numerical data, and the subtle nuances of the situation. We will scrutinize what the data unequivocally indicates, explore its potential interpretations, and contemplate the implications if this object is indeed behaving as it appears to be. We will venture into speculative hypotheses, consider alternative explanations, and explore possibilities that may sound like science fiction but are nevertheless grounded in tangible measurements. By the end of this discourse, you will possess all the requisite information to form your own conclusion. Is this a natural celestial occurrence, a measurement error, or something else entirely? The forthcoming observations hold the key. The period between November and December of 2025 represents the critical window. This is when 3I Atlas will be observable once more, at its closest approach to Earth on December 19th, when telescopes worldwide will be trained upon it, actively seeking evidence of that elusive debris cloud. If it is detected, the enigma will be resolved. If it remains absent, the mystery will escalate into something far more significant. Let us commence by establishing a timeline, by discussing the circumstances of its discovery, the data we have collected, and the reasons why these measurements are instigating such widespread concern within the astronomical community. Part 2. Latest Breaking Observations. The narrative commences on July 1, 2025, when a telescope situated in Chile, part of the Asteroid Terrestrial Impact Last Alert System, detects a faint streak of light traversing the constellation Aquarius. The Atlas system is designed to identify near-Earth objects, specifically asteroids that might pose a threat. However, this particular detection is distinct. Within hours of the initial observations, astronomers realize they are observing something that defies conventional understanding. Its orbital path is aberrant, its velocity is anomalous, and its trajectory curves in a manner indicative of an origin beyond our immediate cosmic vicinity. The data is re-evaluated, potential errors are investigated, and confirmations are sought from other observatories. By the end of that week, the conclusion is definitive, a hyperbolic trajectory, signifying an interstellar origin. This marks the third such confirmed object, following Oumuamua and Borisov. The designation is assigned 3I Atlas, with the I denoting its interstellar nature, akin to a cosmic passport stamp signifying "not from this locale." However, unlike Borisov, which adhered to expected cometary behavior, 3I Atlas immediately begins to exhibit signs of strangeness. Its orbital path is retrograde, moving in opposition to the solar system's overall rotation, yet it maintains an unusually close alignment with the ecliptic plane. This is highly unusual. Interstellar objects are generally expected to approach at random angles, given that space is three-dimensional and lacks a preferential direction. The fact that 3I Atlas is closely following the plane where planets orbit suggests either an extraordinary coincidence or a deliberate influence. Furthermore, consider the timing. The object crosses the ecliptic plane 26 days prior to reaching perihelion. It then passes near Mars, followed by Venus. Subsequently, it reaches its closest point to the Sun on October 29th, 25, a mere 8 days after solar conjunction, a period when the object was obscured from Earth's view by the Sun itself. This precise alignment, this orchestrated sequence of close encounters and solar concealment, raises considerable concern. While not impossible, it represents an exceptionally tight temporal window. Its perihelion distance is approximately 0.1 astronomical units, which translates to roughly 15 million kilometers from the Sun. This is close enough for the surface temperature to vaporize most materials, close enough that any comet would be expected to expel gas and dust in a spectacular fashion. And indeed, 3I Atlas does display activity. A coma, a diffuse envelope of gas, surrounds its nucleus. Spectroscopic analysis reveals carbon dioxide as the predominant component, which is not inherently unusual. However, what follows is perplexing. Astrometric measurements begin to arrive from instruments such as the Atacama Large Millimeter, Submillimeter Array, or ALMA, renowned for its precision in positional astronomy. These measurements compare the observed position of 3I Atlas near perihelion with its predicted position, calculated solely based on gravitational forces exerted by the Sun and planets, considering all known factors. A discrepancy of approximately 4 arcseconds is detected. This may seem insignificant. An arcsecond is 1/3600th of a degree, and 4 arcseconds is roughly equivalent to the width of a human hair viewed from across a football field. However, in the realm of astrometry, 4 arcseconds represents a substantial deviation, a significant divergence. It signifies a clear departure from the expected position, indicating that something is influencing its trajectory. When this offset is incorporated into dynamical models, an attempt is made to ascertain the force responsible for this deviation. The resulting calculation is profoundly alarming. It points to a non-gravitational acceleration, meaning the object is increasing its speed or altering its direction by means of a force beyond gravity. The sole natural explanation for this is outgassing, the expulsion of material from the comet, generating a propulsive effect. This is how comets typically function. They are composed of ice, rock, and dust, frozen together for eons. As they approach the sun, solar heat vaporizes the ice. Water ice, carbon dioxide ice, methane, ammonia, and other volatile compounds begin to boil off. This released gas carries dust particles with it, creating jets, tails, and a luminous coma, and importantly, generating thrust. The material expelled in one direction propels the comet in the opposite direction in accordance with Newton's third law of motion, action and reaction. Every comet that ventures near the sun experiences this phenomenon. It is one of the fundamental principles of cometary physics. The critical factor is the scale of this process. The amount of material that needs to be expelled to produce a specific acceleration is contingent upon the comet's mass, the velocity of the ejected material, and the geometry of the jets. However, for an object the size of 3I Atlas, traveling at its observed velocity and deviating from its predicted path by 4 arcseconds during its perihelion passage, the numerical outcomes are unambiguous. A substantial mass loss is required, not a minor one, but a significant quantity. And this is precisely where the enigma intensifies. The visible coma surrounding 3I Atlas, the gas and dust that can be observed and measured, does not account for a mass loss remotely sufficient to explain the observed acceleration. There is observable activity, yes. Outgassing is occurring, undoubtedly. But the extent is insufficient by orders of magnitude. If the acceleration is genuine, if those 4 arcseconds accurately reflect the object's behavior, then it should have expelled a quantity of material on the order of 5 billion tons, possibly more. This is a conservative estimate. Some models suggest an even higher figure, 5 billion tons. To provide perspective, a typical long-period comet, such as Halley's Comet, one of the most luminous comets in recent history, expelled perhaps tens of millions of tons of material during its perihelion passage. If one is generous, this figure might extend to 100 million tons. 3I Atlas would have needed to expel 50 to 100 times that amount, representing one of the most violent outgassing events ever recorded. And when a comet undergoes such an event, the consequences are visually apparent. There are pronounced surges in brightness that persist for weeks. Tails extend for millions of kilometers. A debris cloud becomes visible, illuminated by reflected sunlight and thermal emissions, observable from Earth-based and spaceborne telescopes. So, where is this evidence? Where is the debris cloud? Where is the immense tail? Where is the photometric signature of all that material being propelled into space? Some observations indicate increased brightness, and some detect jets. But these phenomena are nowhere near what would be expected for a mass loss of 5 billion tons, not even remotely close. And therein lies the discrepancy, the unmistakable red flag. A force without a visible cause, an acceleration without the requisite reaction mass to explain it. There are several potential resolutions to this paradox. It is possible that we are observing at the wrong time and the debris cloud exists, but has not yet become detectable. Alternatively, its orientation might render it difficult to observe from Earth, or the material may have been ejected in a direction currently obscured from our vantage point. Geometry and viewing angle are crucial factors, and our understanding of the three-dimensional structure of the phenomena surrounding this object is limited. Another possibility is that the material is present but is inherently dark, perhaps consisting primarily of gas rather than dust, and gas does not reflect sunlight effectively. It could also be composed of particles too small or too transparent to be detected by our instruments. It is conceivable that we are underestimating the potential stealth of a debris cloud. However, these speculative possibilities are accumulating, and with each new observation, each new spectrum, each new image, astronomers are progressively narrowing the range of potential explanations. The window of opportunity for the "we simply haven't seen it yet" hypothesis is rapidly diminishing, leaving us with the more uncomfortable alternative, that the object accelerated without expelling the anticipated mass. Perhaps it is performing an action that eludes our current comprehension. Perhaps the rules are fundamentally different for this interstellar visitor, and if that is the case, the pertinent question then becomes, what else is different? What other aspects of our understanding might be incorrect? Because an object capable of altering its motion without the expected reaction mass is not merely a scientific curiosity. It represents a fundamental challenge to the very foundations of our understanding of motion, momentum, and the behavior of matter in the cosmos. It is an anomaly that has the potential to either revolutionize a scientific field or derail the careers of those who attempt to explain it. Observations are ongoing. Telescopes are tracking the object as it completes its trajectory around the Sun and heads back into the outer reaches of the solar system. The months of November and December of 2025 are prominently marked on every astronomer's calendar. This period signifies 3I Atlas's closest proximity to Earth, approximately 19 million kilometers away on December 19th. It is at this juncture that the viewing geometry will be optimal, affording us the most favorable opportunity to detect the debris cloud, should it exist. This will allow us to measure its brightness, spectrum, and morphology, ultimately answering the critical question: is this an exceptionally unusual natural comet, or is it something else entirely? However, before we reach this December deadline, and before we contemplate the potential ramifications of future discoveries, it is imperative that we fully grasp the quantitative data. We must present concrete figures, meticulously review the calculations, and precisely delineate the magnitude of this discrepancy and what would be required to resolve it. Because numbers, while potentially incomplete or misinterpreted, do not inherently deceive. And the numbers associated with this phenomenon are, quite frankly, astonishing. Part 3. Quantitative implications of the claim. Let us now address the concept of momentum, not in a motivational context, but in its physical sense. Momentum is defined as the product of mass and velocity. To alter one's momentum, a force must be applied. And if that force is generated by the expulsion of material, as in the case of a rocket or a comet undergoing outgassing, then the momentum gained is precisely equal to the momentum of the ejected substance. This principle, the conservation of momentum, is one of the immutable laws of physics. It cannot be circumvented or negotiated. It is a fundamental constant. Therefore, when we assert that 3I Atlas has undergone a non-gravitational acceleration, what we are truly conveying is that its momentum has been altered in a manner that cannot be explained by gravity alone. And when we attempt to quantify the amount of material that would need to be expelled to effect this change, we encounter a figure that is incongruous with our current observations. Here is the foundational information. The estimated mass of the object ranges between 10 billion and 100 billion kilograms. This is a preliminary estimate, as the precise density and size are not definitively known. It is likely several kilometers in diameter, possibly less, possibly more. The margin of uncertainty is considerable. Let's consider a moderate estimate, proposing 50 billion kilograms, which equates to 50 million tons. This represents a substantial comet nucleus. The observed positional deviation near its closest approach to the Sun, or perihelion, is approximately 4 arcseconds. Over the entire period of a perihelion passage, taking into account the orbital mechanics, this deviation corresponds to a change in velocity of roughly a few meters per second. Let's use 5 meters per second as an approximate figure. This might seem insignificant. 5 meters per second is akin to a brisk walking pace, about 11 miles per hour. However, when dealing with an object weighing 50 million tons, even a minor alteration in speed necessitates an immense transfer of momentum. Now, when a comet outgasses, the material it expels possesses a certain velocity relative to its core. For typical comet jets, this velocity falls within the range of a few hundred to a few thousand meters per second. Let's assume a value of 1,000 meters per second, which is a reasonable middle ground assumption. Therefore, if you aim to alter the velocity of a 50 million ton comet by 5 meters per second, and the ejected material is traveling at 1,000 meters per second in the opposite direction, you would need to expel approximately 5 billion kilograms of material, or 5 million tons. This figure represents the lower end of the estimate. Should the velocity change be greater, the ejection velocity be lower, or the comet's mass be higher, the required mass loss escalates rapidly. 5 million tons might not sound like a large proportion of 50 million tons, being only 10%. However, when 10% of an object's mass is jettisoned over a period of mere days or weeks, it does not occur discreetly or unnoticed. It creates a dramatic display, forming a vast, luminous, and enduring debris cloud. Upon examining images of 3I 2025 S1 Atlas from late October and early November of the year 2025, no such spectacular event is evident. Wait, 5 million tons? I previously mentioned 5 billion. What's the discrepancy? The uncertainty inherent in these estimations is considerable. The comet's mass is not precisely known. The velocity alteration is subject to estimation. The speed at which material is ejected is also uncertain. Some theoretical models, depending on the input parameters, suggest a required mass loss of up to 5 billion tons or more, representing a 100-fold increase. Why such a wide range of possibilities? Because the underlying physics is highly sensitive to the geometric configuration. If the jets are all directed uniformly, the efficiency of momentum transfer is maximized. Conversely, if they point in random directions, a significantly greater amount of material must be expelled to achieve the same net propulsive force. The nature of the expelled material also plays a role. If it is predominantly gaseous with minimal dust content, the efficiency shifts. Furthermore, if the nucleus is rotating, the jets will activate and deactivate cyclically, averaging the thrust differently over time. Consequently, the precise quantity of mass loss required for the observed acceleration remains unknown, but it is understood to be substantial. It is greater than what the current visible coma and tail indicate. Moreover, typical comets within our solar system exhibit clear signs of mass loss when experiencing non-gravitational accelerations, such as increased brightness, extended tails, dust clouds, and fragmentation events. All the dramatic phenomena expected when a comet sheds a significant portion of its mass. Let us draw a comparison with some documented instances. Comet Hale-Bopp, one of the most active comets in recent history, expelled approximately 10 million tons of dust and 100 million tons of gas during its perihelion passage in the year 1997. The resulting debris cloud was immense, visible to the naked eye for several months. Comet Hyakutake, another remarkable visitor, displayed similar levels of activity. These serve as benchmarks, representing what is considered normal for a highly active comet. If 3I 2025 S1 Atlas expelled 5 billion tons, that would be 50 times more than Hale-Bopp. Even if it expelled 5 million tons, that would still be comparable to a major comet. In either scenario, we would anticipate observing something dramatic: a tail extending for millions of kilometers, a bright and expansive coma, spectroscopic evidence of freshly released volatile compounds, perhaps even signs of fragmentation, with chunks of the nucleus breaking off and creating secondary sources of activity. All of these phenomena are detectable with modern telescopes and should be readily apparent if the mass loss occurred on the scale suggested by the acceleration. To be fair, some observations do indicate increased activity. There are reports of jets, bursts of brightness, and expansion of the coma. However, this is insufficient by a factor of 10, 50, or 100, depending on which model is considered. The photometric brightness, which is the amount of sunlight reflected by the dust and gas, is elevated but not extraordinarily so. The tail, while present, does not constitute a massive structure. Spectroscopic analysis reveals outgassing, yes, but not a catastrophic release of material. Therefore, what are the possible explanations? Firstly, we might be failing to observe the debris cloud. It could be present, but for some reason we have not yet detected it. Perhaps it requires time to disperse and become visible. The viewing angle might be unfavorable, leading us to observe it from an unsuitable perspective. Alternatively, the particles might be minuscule and transparent, scattering very little light. This is the hypothesis of a natural comet with unusual visibility characteristics. It is the most conservative explanation, requiring no new physics, merely patience and enhanced observational capabilities. Secondly, the acceleration is genuine, but the mass loss is occurring with greater efficiency than our current understanding suggests. It's possible the ejected material is moving at a higher velocity than we anticipate. Perhaps the jets are exceptionally well collimated or precisely aligned to maximize thrust. There might be unusual chemical reactions occurring involving volatile ices that sublimate rapidly without producing significant dust. This is the hypothesis of an exotic yet natural comet. It pushes the boundaries of our models but does not invalidate them. Thirdly, the acceleration is not attributable to outgassing at all. It could be radiation pressure acting on a structure with very low mass or high reflectivity. It might involve some interaction with plasma and the solar wind. It is also conceivable that gravitational lensing or a measurement error is creating the illusion of an offset when none exists. This is the hypothesis that we are misinterpreting the measurements. This is a plausible scenario, as errors can occur in scientific endeavors. However, the measurements have undergone rigorous verification and re-verification. The offset is indeed real. The question remains, what is its cause? Fourthly, the object has accelerated without expelling the anticipated mass. It has altered its momentum through an unknown mechanism. Perhaps it is employing a propulsion system. It could be leveraging some interaction with the solar magnetic field or the solar wind in a manner not observed in natural objects. It might be exhibiting behavior that mimics outgassing but is fundamentally different. This is the hypothesis that something is fundamentally amiss, the one that causes considerable concern. If this hypothesis holds true, then our entire understanding of cometary physics may be incomplete, or worse, deliberately misleading. Subsequent observations scheduled for November and December of the year 2025 are expected to help narrow down these possibilities. If a substantial debris cloud becomes apparent, the first explanation gains credence. If ultra-efficient jets with unusual chemical properties are detected, the second hypothesis is supported. Should a measurement error or calibration issue be identified, the third scenario would be favored. If none of these outcomes materialize, we are left contemplating the fourth possibility. And it is within this fourth scenario that matters become exceptionally intriguing or perhaps alarming, depending on one's perspective. However, the numerical data alone do not fully convey the extent of the strangeness. We must consider the implications of this discrepancy, why it transcends a mere puzzle and serves as a warning sign pointing towards something profound, something that connects with the other 9 anomalies, suggesting this object is not adhering to the same principles as other celestial bodies observed originating from interstellar space. Part 4. The red flag of discrepancy. There is a distinction between something being unusual and something being incorrect. An object tumbling without a visible tail, like Oumuamua, is unusual. A comet with an atypical composition is unusual. An orbit with a low probability is unusual. These are occurrences that prompt further investigation, additional tests, and research papers with question marks in their titles. But incorrect? Incorrect implies that the foundational laws you rely upon are beginning to bend. When the principles of action and reaction appear decoupled, when an object behaves in a manner that contradicts the physics you have dedicated your career to studying. The 10th anomaly falls into this latter category. And here is why. Every other anomaly discussed thus far, from its trajectory to its composition and brightening behavior, can be explained by extending our current understanding of physics. Perhaps the object formed in an atypical environment. It might have traversed interstellar space for millions of years, with cosmic radiation altering its surface. The viewing angle during its brightening phase could have made it appear stranger than it actually was. These explanations require us to stretch our models to encompass edge cases and acknowledge a greater diversity in the universe than we previously assumed. However, they do not necessitate discarding our existing models entirely. The discrepancy in acceleration is different. If 3I 2025 S1 Atlas genuinely altered its velocity without expelling the expected mass, then one of the following must be true. Either our understanding of momentum conservation is flawed, which would fundamentally challenge 3 centuries of physics, or the object is employing a mechanism previously unknown to us, be it natural or otherwise, or we are fundamentally misinterpreting the measurements, which, while embarrassing, would still be correctable. The first option is highly improbable. The second is unsettling. The third represents the hope that most are clinging to. Allow me to offer an analogy. Picture witnessing a rocket launch. The rocket ascends, accelerates, and climbs skyward. You understand the process completely. The rocket consumes fuel, expels hot gases backward, and this reaction propels the rocket forward. A clear demonstration of Newton's third law. Now, imagine the rocket lifting off, accelerating and climbing, but with absolutely no exhaust visible, no flames, no smoke, no gas, simply the rocket moving upward and increasing its speed. You would be astounded. You would scrutinize your instruments, questioning your sanity, because propulsion without exhaust defies the fundamental principles of physics, indeed, of all known physical phenomena. This is potentially what we are observing with 3I 2025 S1 Atlas. Propulsion without discernible exhaust, or at least exhaust so faint or concealed that it remains undetectable. The reason this constitutes a red flag, and is more alarming than peculiarities in composition or trajectory, is that it violates a principle more fundamental than any specific model of cometary formation: the conservation of momentum. If you exert a force on an object, it exerts an equal and opposite force back. If you change your velocity, you must expel something in the opposing direction. There are no exceptions, except, perhaps, there are. Let us clearly delineate the two mutually exclusive possibilities. Possibility 1. The debris cloud is present, but we are simply not seeing it yet. It might be too faint. Its orientation could be edge-on, causing us to view it through its thinnest dimension. The particles might be dark and small. The mass loss could have occurred in a brief burst, and the cloud is still expanding and has not yet reached a detectable luminosity. This possibility upholds the established laws of physics. It suggests the object is a natural comet, albeit an extreme one, and our understanding will improve with more comprehensive data. Possibility 2. There is no debris cloud. The object accelerated through an alternative mechanism. Perhaps it is utilizing solar radiation pressure, though this would necessitate a surface area-to-mass ratio that seems improbable for a solid entity. It might be interacting with the solar wind, but this force is weak and unlikely to account for the observed acceleration. It could be venting gas without dust, rendering it invisible to our instruments, yet still carrying momentum. Or, and this is where speculation becomes disquieting, it could be employing a propulsion system, a device intentionally engineered to generate thrust, something artificial. Now, before I am accused of leaping to conclusions about extraterrestrial origins, let me clarify. The second possibility encompasses numerous scenarios that remain within the realm of natural phenomena. These include exotic chemistry, unusual physics, or edge cases of cometary behavior that we have not previously encountered. However, it also includes the possibility, the elephant in the room, that no one wishes to seriously discuss due to its science fiction connotations, that 3I 2025 S1 Atlas is not entirely natural, that it is, at least in part, engineered, and that something, somewhere, constructed it and dispatched it into our solar system. I recognize how this sounds. I understand the immediate impulse is to dismiss it as conspiratorial thinking. However, the scientific method does not operate by dismissing possibilities simply because they are uncomfortable. Science proceeds by following the evidence wherever it leads and rigorously testing every hypothesis that aligns with the data. And if the data indicate the absence of a debris cloud, then we must confront the implications, even those that seem more suited to a cinematic narrative. The other anomalies exacerbate this concern. If 3I 2025 S1 Atlas were solely exhibiting anomalous acceleration, we could attribute it to measurement error or unusual outgassing. However, it also follows an improbably aligned trajectory. Its composition differs from that of typical comets. Its brightening and jet production occur in a manner that seems counterintuitive. Furthermore, it originates from the same direction as a notable, unexplained radio signal. Each anomaly in isolation is peculiar but potentially explainable. When viewed collectively, coupled with an acceleration that lacks the expected debris cloud, it begins to resemble a pattern rather than mere coincidence. This is precisely what renders the 10th anomaly the most unsettling. It is not merely an additional item on a list. It is the keystone supporting the entire arch. If it proves to be accurate, and if subsequent observations confirm that the object accelerated without observable mass loss, then all the other anomalies transform from quirks into crucial clues. Clues that point toward something for which we may not yet be prepared. Something that would compel us to reevaluate not only cometary physics, but the very nature of what we might encounter in the vastness of interstellar space. This brings us to the stakes involved. Why does this matter? Why should anyone concern themselves with the slight deviation in course of an icy rock from another star system? Because the answer to this question dictates our perception of what is possible. It determines whether we inhabit a universe governed solely by impartial natural forces or whether there are other intelligences observing, traveling, and exploring alongside us. It influences whether our understanding of physical laws is complete or if significant portions remain undiscovered. Ultimately, it shapes our perspective on our own place within the cosmos. So, what transpires next? What are we awaiting? And what will be the implication if the December observations do not reveal the debris cloud? Part 5. What is at stake? Why should we care? Science is not merely a collection of facts. It is a dynamic process, a method of inquiry, and a commitment to accepting findings, even when they are unwelcome. Occasionally, this process leads to conclusions that fundamentally alter our understanding. For instance, the realization that Earth orbits the Sun rather than the reverse, or the discovery that time itself dilates at relativistic speeds, or the understanding that the universe is expanding and will eventually succumb to a cold, dark end. These are not comforting revelations, yet they are truths, and embracing them grants us power, the power to predict, to comprehend, and to navigate a reality that remains indifferent to our comfort. 3I 2025 S1 Atlas represents such a pivotal question, not because it is definitively artificial, nor because it constitutes irrefutable proof of extraterrestrial life, unknown physics, or any specific conclusion, but because it compels us to confront the boundaries of our knowledge. And the resolution, whatever it may be, will inevitably expand those boundaries. If the follow-up observations in November and December of the year 2025 reveal a substantial debris cloud, if 5 billion tons of ejected material are detected, if the mass loss aligns with the observed acceleration, and if all pieces fall neatly into place, then here is what we will learn. We will learn that interstellar objects can be far more extreme than we had previously imagined. We will understand that cometary formation can occur in environments vastly dissimilar to our own solar system. We will recognize that the universe exhibits a greater diversity than our current models can account for. This would still be a momentous discovery. It would signify a comet that defies all existing classifications, a visitor from an alien star system offering new insights into planetary formation, stellar evolution, and the chemical composition of the interstellar medium. It would broaden the scope of planetary science, providing a new data point, a new benchmark, and a novel object for study and comparison. However, if the observations fail to detect the debris cloud and the acceleration remains unexplained by visible mass loss, then we enter entirely different territory. We will be forced to pose more challenging questions. Could there be an unknown mechanism of propulsion? Is there a way for a natural object to gain velocity without shedding mass? Is there an interaction between the object and its solar environment that generates thrust in a manner previously unobserved? Or are we potentially observing something that is not entirely natural, something that was deliberately constructed, designed, and dispatched with a specific objective? The implications would ripple outwards like fissures in ice. For models of cometary formation and evolution, we would either need to develop new physical principles or accept that some objects operate under distinct rules. In the study of interstellar objects, we would realize that Oumuamua might not have been the singular anomaly we once believed. Perhaps atypical objects are the norm, and what we consider normal comets are merely the placid local variants, with the rest of the galaxy employing a different set of operational guidelines. For planetary defense, the ramifications would be more immediate and concerning. Currently, our tracking of asteroids and comets relies on gravitational models, enabling us to calculate orbits decades in advance and predict close approaches with remarkable accuracy. However, if objects can accelerate unpredictably, if they can alter their course without warning or discernible cause, then our tracking systems possess a critical blind spot, potentially a fatal one. One cannot defend against an entity if its future trajectory is unknowable. And if 3I 2025 S1 Atlas is indeed exhibiting such behavior, then other objects might possess similar capabilities. This is not a comforting thought when the objective is to safeguard a planet populated by individuals who do not typically contemplate the threat of celestial bodies from outer space. Then there is the philosophical, the existential dimension. For the majority of human history, we have operated under the assumption of our uniqueness, not necessarily in terms of superiority, intelligence, or importance, but simply because we are present, conscious beings, and as far as we can ascertain, no other entities in the universe are paying attention. The silence of the cosmos has been profound. We have transmitted signals. We have strained to hear responses. We have surveyed thousands of stars for evidence of technology and found nothing. The universe appears devoid of life, inert and indifferent. But what if it is not empty? What if the silence is merely a consequence of our inability to discern the correct signals? What if the technological signatures we seek do not manifest as radio transmissions or colossal structures, but as objects traversing space in ways that defy conventional physical explanations? What if beings elsewhere are exploring the galaxy in a manner akin to our own planned endeavors, dispatching probes, collecting data, charting their surroundings? And what if 3I 2025 S1 Atlas is one such probe? This is not mere idle speculation. It is a hypothesis that a segment of the scientific community is taking seriously, not out of a desire to believe in extraterrestrial life, nor out of abandonment of naturalistic explanations, but because the collected data are leading in a direction that cannot be disregarded. When presented with 9 individually improbable anomalies, coupled with a 10th anomaly that appears to contradict fundamental principles of physics as we understand them, one must at least entertain the possibility that we are not observing a comet. We might be observing something else entirely. For the general public, for those outside the fields of astronomy and physics, this distinction is significant in a different way. It challenges the narrative we have constructed about our place in the universe and what lies beyond. Most individuals proceed through life with the understanding that the universe is vast, empty, and that we are alone. That fundamental belief profoundly influences every aspect of our existence. It dictates our perceptions of significance, our search for purpose, and our vision for the future of humanity. Should that foundational belief prove erroneous, if we are indeed not solitary, if other sentient beings are traversing our solar system with their crafts, then the entire narrative of human civilization is irrevocably altered. We would transition from protagonists to mere supporting players in a far grander cosmic play. This realization is either profoundly unsettling or incredibly inspiring, depending entirely on one's inherent disposition. So, what precisely are we anticipating? We are awaiting the arrival of light. Photons, bouncing off particulate matter, expelled by gaseous emissions, dispersed by fragmented debris. We are awaiting the moment when our advanced observatories, specifically pointing towards 3I Atlas in November and December of the year 2025, will capture the visual evidence confirming or disproving the existence of this debris cloud. We anticipate spectroscopic analysis to illuminate the processes occurring in close proximity to the object's nucleus. We await astrometric data to either substantiate or invalidate the observed acceleration measurements. In essence, we are waiting for the universe to reveal its hidden hand. The time frame is precisely delineated. The celestial body is scheduled to reach its closest proximity to Earth on the 19th day of December, 2025. This specific window represents the optimal period for observation. It is at this juncture that sophisticated instruments such as the James Webb Space Telescope, the Hubble Space Telescope, the Atacama Large Millimeter, Submillimeter Array, ALMA, and various terrestrial observatories will possess their greatest opportunity to ascertain the true nature of the phenomenon. Their scrutiny will be focused on identifying definitive indicators. These include an expansive dust tail, a radiant coma, and discernible fluctuations in brightness consistent with significant material ejection. Additionally, they will be searching for spectral lines indicative of recently liberated volatile compounds, evidence of fragmentation events, and any radio emissions. Any signal that unequivocally declares this is indeed a comet, albeit an exceptionally peculiar one. The presence of these signatures would resolve the enigma. Their absence, however, would deepen the mystery, potentially leading to a fundamental reevaluation of our cosmic perspective. And here's the remarkable aspect. Our wait will not be protracted. The observational data is currently being gathered. By the time this narrative reaches you, some of the preliminary findings may already be available. Regardless of the ultimate outcome, the answer is poised to be one of the most momentous scientific revelations of this decade, perhaps even of this century. Therefore, before we delve into the intricate details of its composition, trajectory, and the myriad unusual characteristics, let us first acknowledge the profound implications at play. We are not merely discussing an astronomical anomaly. We are examining a pivotal case study that will challenge our fundamental understanding of motion, mass, and the nature of extraterrestrial visitors. This is a critical juncture where scientific inquiry will either venture into uncharted territories or reinforce established knowledge. And we are contemplating the distinct possibility, however improbable, that we are on the cusp of the first confirmed instance of detecting an entity from beyond our solar system that did not arrive by chance. This is the essence of its importance. This is why the 10th anomaly transcends mere curiosity. It represents a gateway, and in November and December of the year 2025, we will discover what lies beyond. Part 6. Detailed Composition and Anomalous Chemistry. Let us immerse ourselves in the intricacies. Let us scrutinize the very substance of this object, for it is within its elemental makeup that the perplexing nature of this phenomenon first became apparent, long before any anomalies in its acceleration were detected. When astronomers analyze the light emanating from a comet, dissecting it into its constituent wavelengths and observing the dark lines where specific molecular structures absorb particular colors, they are essentially reading a unique chemical signature. Each molecule possesses an individual spectral fingerprint. Water absorbs at one point, carbon dioxide at another, cyanide manifests at a specific wavelength, and sodium at yet another. It is akin to scanning a barcode that reveals the object's elemental composition. The James Webb Space Telescope directed its instruments towards 3I Atlas during August and September of 2025. The JWST is specifically engineered for such analytical tasks. Its exceptional sensitivity in the infrared spectrum enables the detection of molecules that remain invisible to optical telescopes. What it uncovered deviated significantly from all prior expectations. The ratio of carbon dioxide to water was an astonishing 8-to-1. This is not a misprint. There was 8 times more carbon dioxide present than water. For comparative context, typical comets within our solar system exhibit water as the predominant volatile compound, with carbon dioxide present only as a minor constituent. The usual ratios range from 10-to-1 or even 100-to-1 of water to carbon dioxide. 3I Atlas completely reverses this established norm. It presents as a carbon dioxide-dominant comet with a minimal admixture of water, rather than the inverse. Why is this distinction so critical? Because water ice constitutes the most prevalent volatile substance in the outer reaches of our solar system. It forms the primary component of comets, Kuiper belt objects, and icy moons. The underlying reason is elegantly simple. Oxygen is abundant and hydrogen is abundant. These elements readily combine, and water ice maintains its stability across a broad spectrum of temperatures and pressures. Carbon dioxide, conversely, is less common due to the lesser abundance of carbon compared to hydrogen. Furthermore, carbon dioxide ice sublimates at elevated temperatures, indicating its inherent instability. For an object to be exceptionally rich in carbon dioxide, it must have originated in an environment where water is suppressed and carbon dioxide is preferentially concentrated. Such conditions are atypical, suggesting formation within a frigid, carbon-rich zone. This could be a molecular cloud situated far from any stellar influence, or perhaps a protoplanetary disk exhibiting unusual chemical properties, or even a region for which our current theoretical models are insufficient. However, the peculiarities do not cease there. The water that is present, accounting for approximately 4% of its mass, is also behaving in an unconventional manner. Its production rate is remarkably low. The object is demonstrably active. It is generating a coma and exhibiting outgassing. Yet, the volume of water vapor being released is substantially less than one would anticipate for an object of its magnitude situated at its current distance from the Sun. This anomaly suggests either that the water ice is deeply concealed beneath a substantial layer of non-volatile material, or that there is simply a paucity of water to begin with. Both scenarios are highly unusual and necessitate explanations that diverge from conventional cometary models. Then there is the matter of its polarization. When light reflects off a surface or scatters from particulate matter, it becomes polarized. The degree of polarization is intrinsically linked to the size, shape, and composition of the particles, as well as the angle from which they are observed. Typically, comets exhibit positive polarization across most phase angles, indicating a specific orientation of the reflected light. 3I Atlas, however, displays extreme negative polarization, reaching a minimum of approximately 2.7% at a phase angle of 7 degrees. This characteristic is unprecedented among known comets. It implies that the particles suspended within the coma are either exceptionally minute, possess an unusual refractive index, are configured in a peculiar manner, or a combination of these factors. Polarimetric imaging serves as a highly sensitive probe of surface properties capable of revealing information that spectroscopic analysis cannot. The data gathered from 3I Atlas indicates that the material surrounding this object is not typical cometary dust. It suggests something entirely different. Perhaps it comprises pure carbon dioxide ice grains, or a complex organic polymer formed through interstellar radiation, or even metallic particles with unconventional geometries. While the precise composition remains elusive, the data unequivocally demonstrates what it is not. It is not the silicate and organic mixture commonly observed in all other comets. Furthermore, we encounter the issue of metals. Preliminary spectroscopic reports, which are still provisional and not yet fully corroborated, suggest anomalous metallic ratios. Specifically, nickel appears to be elevated in proportion to iron. In comets originating from our solar system, nickel and iron are typically found in proportions closely mirroring cosmic abundance ratios, approximately 1 part nickel for every 16 parts iron. However, certain observations of 3I Atlas hint at ratios approaching 1 to 1, or even a dominance of nickel. If these findings are indeed accurate, and this is a significant qualification due to the low signal-to-noise ratio and ongoing analysis, this would represent an extraordinarily peculiar situation. Nickel-rich alloys are not typically expected to form through natural condensation processes within a protoplanetary disk. They are more characteristic of processed materials, industrial alloys, and refined metals. Now, before the imagination runs wild and conjures speculative theories, it is imperative to emphasize that these metallic measurements are not yet definitively confirmed. They could stem from instrumental artifacts, contamination from other celestial objects within the line of sight, or misinterpretations of spectral features that superficially resemble nickel, but are, in fact, something else entirely. The scientific method demands rigorous skepticism, particularly when confronted with extraordinary claims. Nevertheless, the very fact that these signals are being discussed and that credible scientists are giving them sufficient consideration to publish papers and request further investigation underscores the profoundly atypical nature of this object. So, what potential explanations exist for this peculiar composition? Let us explore the possibilities, progressing from the most conventional to the most speculative. Firstly, the object may have coalesced in an extremely cold, carbon-rich environment, far removed from any stellar influence. Interstellar molecular clouds can harbor pockets of unique chemical compositions. If 3I Atlas formed within such a region, it might have incorporated a greater abundance of carbon dioxide and a lesser amount of water than is typical for comets within our solar system. Over millions or billions of years, cosmic radiation could have altered its surface, resulting in the anomalous polarization signature observed. This represents a naturalistic explanation that requires no new physical principles, only an unfamiliar cosmic environment. Secondly, the object could be an ice dwarf originating from the outer reaches of another star system. Certain theoretical models posit that planetary systems can eject vast quantities of smaller bodies during their formative stages, propelling them into interstellar space. If 3I Atlas originated from a system with distinct elemental abundances or a different thermal history, its composition might reflect these divergences. This explanation is also naturalistic, but necessitates an expansion of our models of planetary formation to accommodate a broader spectrum of chemical diversity. Thirdly, the object may have undergone extensive processing due to interstellar radiation and cosmic rays. A journey of several million years through the galaxy, exposed to high-energy particles, would inevitably lead to the fragmentation of molecules, the creation of novel compounds, and alterations to surface properties. What we are observing might be the consequence of this processing, a pristine water-ice comet transformed into something else by the harsh conditions of interstellar space. This hypothesis holds a certain appeal as it accounts for the observed anomalies while remaining within the realm of natural phenomena. Fourthly, and this marks our entry into speculative territory, the object's composition could serve as an indicator of an artificial origin. If one were to construct a spacecraft designed for interstellar travel, water ice would likely not be the primary construction material. A more stable substance, one less prone to sublimation and capable of withstanding significant temperature fluctuations and radiation, would be preferred. Carbon dioxide ice, for instance, is a suitable candidate for propellant or coolant due to its clean sublimation process and absence of residue. Nickel alloys are commonplace in aerospace engineering due to their inherent strength, heat resistance, and relatively low density. If 3I Atlas were an engineered construct, its composition might be more readily comprehensible than if it were a natural formation. However, a critical caveat must be underscored. Compositional anomalies alone do not constitute definitive proof. Peculiar chemical interactions can occur naturally. The universe abounds with poorly understood environments, unexplored processes, and edge cases that yield unexpected outcomes. One cannot simply observe an unusual carbon dioxide to water ratio and leap to the conclusion of extraterrestrial construction. Such reasoning contravenes the principles of scientific methodology. Multiple independent lines of evidence are required. Naturalistic explanations must be exhaustively ruled out first. It must be demonstrated not merely that the phenomenon is unusual, but that it is impossible to explain through natural means. It is in this context that the compositional anomalies function as one element of a larger puzzle rather than a standalone solution. They are pieces of a mosaic that also incorporates peculiarities in its trajectory, its luminous behavior, and, most crucially, its unexplained acceleration in the absence of discernible debris. Each individual anomaly might be perplexing, but when considered collectively, they begin to form a coherent pattern, and it is this pattern that commands our focused attention. The overarching conclusion derived from the compositional analysis is unequivocal. 3I Atlas is not a typical comet. Its constituent materials differ, its behavior deviates from the norm, and it defies categorization within established classifications. Whether these divergences are attributable to its formation in an atypical location, modifications incurred during its cosmic journey, or its existence as something other than a comet, remains unknown. However, the chemical anomalies serve as a significant warning signal. When these chemical red flags are combined with dynamical anomalies, a situation arises that necessitates thorough investigation. Consequently, let us now examine the path this object has traversed. Let us deliberate on its trajectory, its timing, and the unsettling coincidences that seem to accumulate with deeper scrutiny. Part 7. Trajectory, Timing, and Fine-Tuning Oddities. In the vastness of space, orbits dictate destiny. An object's trajectory, its past, present, and future course, along with its velocity, is inscribed within the mathematical framework of its motion. Trajectories are immutable. They are governed by the fundamental forces of gravity and momentum, dictated by the initial conditions of an object's formation or expulsion. An orbit can be deciphered like a historical record, revealing its origins, its encounters, and its ultimate destination. The orbit of 3I Atlas, however, is narrating a tale that defies easy interpretation. The object entered our solar system on a hyperbolic trajectory, characterized by an eccentricity exceeding 1. This mathematical signature definitively indicates an interstellar origin. It is not gravitationally bound to our Sun, but is merely passing through. Its inclination is approximately 175 degrees, signifying a retrograde motion, moving in the opposite direction to the orbital paths of the planets. This is not unexpected for an interstellar visitor, as an object from another star system would have no inherent predisposition to align with the orientation of our solar system. Its approach would likely occur at a random angle. Yet, the angle of approach is not entirely random. The orbit exhibits a close alignment with the ecliptic plane, deviating by only about 5 degrees. Geometrically speaking, this is a small deviation, but it is significant. If objects are arriving from arbitrary directions in three-dimensional space, the statistical probability of one coincidentally aligning closely with a specific plane is remarkably low, calculable at approximately 0.2% or 1 in 500. While not statistically impossible, it is hardly a favorable odds proposition. Some astronomers contend that this observation is a result of selection bias. Surveys, such as Atlas, are inherently more sensitive to objects that traverse the ecliptic plane because a substantial portion of their observation time is dedicated to that region. When searching for near-Earth asteroids, observers naturally focus on the vicinity where planets and asteroids are predominantly found, which is near the ecliptic. Therefore, it is plausible that we are simply more likely to detect interstellar objects that happen to pass through this region, even if their prevalence is not disproportionately higher than objects approaching from other angles. This is a valid methodological concern and a reasonable counterpoint, but it does not fully account for the observed alignment. Even when accounting for survey bias, the degree of precision in this alignment remains conspicuously precise. Furthermore, consider the timing of its passage. 3I Atlas approached Mars on the 4th day of October in 2025. While not a direct collision, nor even an exceptionally close encounter by cosmic standards, it was sufficiently near for the gravitational influence of Mars to cause a subtle perturbation in its trajectory. Subsequently, it passed by Venus a few days later, on the 10th of October, followed by its perihelion on the 29th of October. In early November, it made a relatively close pass to Jupiter's orbit. This sequence involves 4 significant solar system bodies encountered within a span of mere weeks. What are the statistical odds of such an occurrence? Certain researchers have conducted simulations, generating thousands of random interstellar trajectories and modeling their passage through the solar system, counting how many happen to pass in proximity to multiple planets in rapid succession. The precise probabilities vary depending on the definition of proximity. However, using reasonable definitions, the likelihood dwindles to approximately 0.005%, or 1 in 20,000. Again, this is not an absolute impossibility, but when compounded with the ecliptic alignment, the cumulative probability becomes exceedingly small. Multiplying small probabilities together results in vanishingly small overall probabilities. Now, this is where the speculative considerations truly begin. Avi Loeb, a distinguished astronomer at Harvard University who has gained considerable notoriety for his openness to considering artificial origins for interstellar objects, has pointed out that the trajectory of 3I Atlas appears remarkably optimized. If one were tasked with surveying the inner solar system, aiming to pass near Mars and Venus, obtain a close observation of the Sun, and then utilize Jupiter for a gravitational assist on the outward journey, one would design a trajectory strikingly similar to this one. The strategy would involve aiming for the ecliptic plane, recognizing it as the locus of celestial interest. The timing of arrival would be calibrated to maximize close encounters, and gravitational assists would be employed to refine the path. This methodology mirrors our own approach when designing missions to explore distant planets. The counter-argument, and it is a substantial one, posits that with a sufficiently large number of celestial objects, rare events are statistically inevitable. If thousands or even millions of interstellar visitors traverse our solar system over time, and we have thus far detected only 3, then it is logical that the detected objects would exhibit unusual characteristics. They would naturally be those that pass sufficiently close to Earth to be observed, and their orbits would direct them into the inner solar system where our telescopes are primarily focused. Selection effects can indeed create the illusion of improbability when the full population of unobserved objects is not taken into account. This is a fair and valid assertion. However, there is an additional detail that renders this trajectory even more suspect. The object reached its perihelion a mere 8 days following solar conjunction. This means that from Earth's perspective, it was obscured by the Sun during its closest approach. For a period of approximately 2 weeks, from mid-October to early November, 3I Atlas resided in a region of space inaccessible to Earth-based observatories due to the Sun's intervening presence. Crucially, perihelion, the moment when a comet typically exhibits its highest activity, characterized by increasing heat, outgassing, and other dramatic cometary behaviors, occurred during this observational blackout window. Is this mere coincidence? Perhaps. The Sun is an immense celestial body, occupying a significant portion of the sky, and any object passing in its vicinity will inevitably be unobservable for a period. However, the timing is exceptionally convenient if one's objective is to evade scrutiny. If the intention were to perform activities near the Sun undetected, the optimal strategy would be to coincide with solar conjunction, waiting until Earth occupied the opposite side of its orbit. And this is precisely what 3I Atlas appears to have done. Now, I am not asserting that this definitively proves anything. I am merely highlighting it as another data point that aligns with a pattern of improbable events that continue to manifest. When confronted with 10 such anomalies, one must question at what juncture the pattern ceases to be a mere coincidence and begins to signify a genuine signal. What is the threshold? How many low-probability events are required before one seriously considers the possibility that they are not independent occurrences but are interconnected? Perhaps there is an underlying reason for their convergence. The peculiarities of its trajectory serve to amplify the enigma of its acceleration. If 3I Atlas were merely exhibiting unusual motion, it could be attributed to measurement inaccuracies, unconventional outgassing phenomena, or random variations. However, its aberrant motion is occurring within a context of alignment with multiple planets, within a specific plane that facilitates observation, and on a schedule that deliberately conceals the most revealing phase of its journey. This involves a confluence of ifs and a remarkable degree of fine-tuning. In nature, such fine-tuning typically implies an underlying cause. Either a selection mechanism is at play, preferentially promoting these particular characteristics, or there is an intelligent agent, a designer, that deliberately chose these specific properties, which brings us to its luminosity and the presence of jets, features that render this object less akin to a typical comet and more suggestive of a phenomenon operating under a different set of protocols. Part 8. Solar-facing brightening jets and anti-tail behavior. Comets invariably increase in brightness as they approach the Sun. This is one of the few universal laws in cometary behavior. The closer an object draws to the solar heat source, the more its ice sublimes, the more material it sheds, and consequently, the more sunlight it reflects. The increase in brightness typically follows a predictable power law relative to the solar distance. For a conventional comet, one might anticipate its brightness to intensify by a factor of 10 for every halving of its distance from the Sun. This behavior is predictable and can be modeled by astronomers with a considerable degree of accuracy. 3I Atlas, however, did not adhere to this established curve. Its brightness escalated at a rate unprecedented among any known comet. Between August and October of 2025, as it drew closer to its perihelion, its photometric brightness surged by several magnitudes within a matter of weeks. This rate of increase can only be described as explosive. That striking brilliance you're witnessing resembles the luminosity seen during a disruptive event where a celestial body's core fractures, exposing pristine ice to solar rays. However, there's no indication of such fragmentation. The object appears entirely whole. So, what could account for this sudden surge in brightness? And here's where it gets even more peculiar. Its hue shifted. Typically, comets exhibit reddish tones, especially when nearing the Sun, because the light reflected is dominated by dust, which inherently leans towards red hues. This is due to elements like silicon, organic compounds, and iron oxides, which absorb bluer light and reflect red. But Comet 3I Atlas unexpectedly turned blue, even more so than the Sun itself. This is counterintuitive, It's the inverse of what we'd anticipate. Blue light signifies reflection or emission within shorter wavelengths, suggesting the presence of either extremely fine particles, intensely hot gas, or a surface characteristic that favors blue over red. One proposed explanation is that the coma is predominantly gaseous rather than dusty. If the outward expulsion consists mainly of carbon dioxide, which generates minimal dust, then the visible light would be fluorescence from gas molecules, not sunlight reflected off particles. Gas fluorescence can indeed appear blue. Carbon dioxide, when ionized by solar ultraviolet radiation, emits at specific blue wavelengths. Therefore, it's plausible that we're observing a comet rich in gas with very little associated dust. While unusual, this isn't entirely outside the realm of possibility. Another theory posits that the surface is highly reflective and smooth, akin to ice rather than rocky. Newly exposed ice can be remarkably bright and possess a faint bluish tint due to its efficient scattering of shorter wavelengths. Perhaps the increased brightness stems from vast expanses of surface ice being suddenly uncovered, either through sublimation, clearing an overlying crust, or via some form of surface regeneration. Again, this is unconventional but not impossible. Then there's the matter of the anti-tail. Cometary tails invariably point away from the sun. This is fundamental physics, as the solar wind and radiation pressure propel gas and dust outward, forming the tail. Occasionally, an optical illusion creates what appears to be an anti-tail, where the tail's orientation suggests it's directed towards the sun, but this is merely a projection effect, with the tail's edge presented to us and our perception being misled. The observations of 3I Atlas, however, reveal what seems to be a genuine jet emanating towards the sun, or at least in a direction not aligned with the usual outward flow. This phenomenon was observed during July and August of 2025, preceding perihelion, when the object was still quite distant. Jets deviating from the antisolar direction are rare but not unprecedented. They can occur if the nucleus's rotation places an active region in an unfavorable orientation, or due to shadowing effects, or if ejected material possesses sufficient velocity to overcome radiation pressure. Nevertheless, they are uncommon and, when coupled with other peculiar characteristics, contribute to the impression that this object defies conventional norms. Let's consider the implications of these observations: a sudden burst of luminosity, a blue coloration, and sunward-facing jets. To model this as a naturally occurring comet necessitates invoking numerous specific conditions: minimal dust, substantial gas production, peculiar surface properties, and active regions in atypical locations. While feasible, constructing such a model requires pushing every parameter to its limit, assuming extreme edge cases for each variable. You might successfully align the model with the data, but it wouldn't feel like a comfortable fit. Conversely, if one attempts to interpret this object as an artificial construct, employing controlled outgassing for propulsion, the observations begin to make more sense. One would anticipate jets not adhering to standard cometary trajectories, as they wouldn't be driven by solar heating. A gas-dominated emission would be expected, as dust is less efficient for propulsion, and maximizing thrust per unit mass would be a priority. Rapid fluctuations in brightness would be logical, reflecting the activation and deactivation of propulsion systems as needed. A blue hue could arise if the propellant is a substance like carbon dioxide or another volatile that fluoresces in blue wavelengths. In this scenario, each unusual feature transforms from a natural anomaly into a deliberate design choice. However, and I cannot emphasize this enough, framing an object as artificial does not inherently make it so. It simply signifies that the artificial hypothesis aligns with the data as effectively as, or even better than, the natural hypothesis. In scientific practice, the selection of a hypothesis is not based solely on which one fits best. It hinges on which hypothesis yields testable predictions and which is more parsimonious. Natural origins possess greater parsimony because we have established evidence of their existence. Artificial origins, conversely, presuppose the existence of something yet to be confirmed, extraterrestrial intelligence capable of interstellar travel. This represents a far more significant assertion, demanding substantially more robust evidence. So, where does this leave us? It leaves us with a collection of observations that are consistent with an atypical natural comet, but also compatible with something more contrived. The means to differentiate between these possibilities lies in scrutinizing the physics, quantifying the acceleration, accounting for all forces, and verifying if the numerical results are coherent. This leads us to the domain of astrometry, gravitational lensing, and alternative explanations for the object's peculiar motion. Part N: Astrometry, Gravitational Lensing, and Alternative Explanations. Astrometry is the discipline dedicated to precisely determining the positions of celestial objects with exceptional accuracy. We're talking about pinpointing an object's location millions of kilometers distant to a fraction of an arcsecond. For context, an arcsecond is roughly equivalent to the apparent size of a quarter viewed from 4 kilometers away. Achieving this level of precision necessitates extraordinarily stable telescopes, meticulous calibration, and sophisticated data analysis techniques. However, when executed correctly, astrometry reveals not only an object's position, but also its movement, and its movement, in turn, indicates the forces acting upon it. The Atacama Large Millimeter Submillimeter Array, or ALMA, stands as one of the premier instruments for this type of investigation. It comprises 66 radio telescopes situated in the Chilean desert, functioning in concert to simulate a single telescope spanning the size of a city. When ALMA was directed towards 3I Atlas near its perihelion, it measured the object's position relative to background stars and quasars. Upon comparison with the predicted position derived from gravitational models, a discrepancy of approximately 4 arcseconds emerged. In astrometric terms, this is a substantial deviation, a veritable chasm. Yet, before drawing definitive conclusions, it is imperative to account for every potential source of error. One of the initial factors to consider is gravitational lensing. As light traverses the vicinity of a massive object, such as the Sun, the very fabric of space-time becomes distorted, and the light follows this curvature. This is a direct manifestation of Einstein's theory of general relativity, a phenomenon predicted by him and subsequently validated by observations during solar eclipses, now a standard tool in astrophysics. The extent of light deflection is contingent upon the proximity of its path to the Sun and the Sun's mass. For light grazing the Sun's limb, the deflection approximates 1.75 arcseconds. For light passing at greater distances, the deflection decreases proportionally with the inverse of the distance. Consequently, when 3I Atlas approached its perihelion, any light reflecting off it and reaching Earth would have been subjected to bending by the Sun's gravitational influence. This bending would alter the apparent position of the object. The crucial question is, by how much? Employing the standard formula, the calculated deflection for 3I Atlas's geometric configuration amounts to roughly 0.27 arcseconds per degree of angular separation from the Sun. At its closest approach to the Sun, the object occupied a very small angular region. Therefore, the lensing effect would be significant, but not to the degree of 4 arcseconds. It might amount to a fraction of an arcsecond at most. The observed offset is an order of magnitude greater than what lensing alone can explain. Could this be an artifact of measurement error? Is it possible that the instruments were miscalibrated or the data analysis flawed? Absolutely. Such possibilities always exist. Astrometry is an inherently challenging endeavor. Systematic errors, atmospheric distortions, instrumental drifts, a multitude of subtle issues can infiltrate the data. However, ALMA is a professional-grade facility. The data have undergone rigorous verification and re-verification. The analytical processes have been subjected to peer review. If an error is present, it is likely subtle and unlikely to manifest as a 4 arc-second offset. Subtle errors typically result in uncertainties measured in fractions of an arcsecond. Thus, if it is neither lensing nor a measurement error, what remains? Non-gravitational acceleration. This implies a force, distinct from gravity, exerting influence on the object, either propelling or retarding it, thereby altering its trajectory in a manner observable as a positional offset. The most natural candidate for such a force is outgassing, material expelled from the comet, generating thrust and consequently modifying its orbit. As previously discussed, the primary challenge here is that the magnitude of outgassing required to account for the observed offset appears to be colossal, and we are not detecting the expected debris cloud that should accompany such an expulsion. However, perhaps other mechanisms are at play. Let us explore them. Firstly, radiation pressure. Sunlight, despite its apparent gentleness, carries momentum. When photons strike a surface, they exert a minuscule force. For an object of exceptionally low mass and extensive surface area, analogous to a solar sail, radiation pressure can become a significant factor. Could 3I Atlas possess insufficient mass or an effective area large enough to be accelerated by sunlight? The quantitative data does not strongly support this. For a nucleus several kilometers in diameter composed of rock and ice, the force exerted by radiation pressure is negligible compared to gravitational forces. Such an object would need to resemble a diaphanous sheet rather than a solid body to achieve meaningful acceleration solely from sunlight. And all available observations point towards 3I Atlas being a coherent mass, not a delicate membrane. Secondly, the Yarkovsky effect. This phenomenon involves a thermal recoil force that influences smaller asteroids. The fundamental principle is that the sunlit side of an object absorbs solar energy, heating up. As the object rotates, this warmed side enters shadow and subsequently cools by radiating infrared energy. The emitted radiation carries momentum, generating a minute thrust. Over extended periods, this effect can alter an object's orbital path. However, the Yarkovsky effect is exceedingly weak. It operates on asteroid-sized bodies over timescales of millions of years. For an object resembling a comet, observed over a period of a few months, the resultant acceleration would be negligible, orders of magnitude too small to account for a 4 arc-second offset. Thirdly, plasma interactions. The solar wind is a continuous stream of charged particles emanating from the sun. If an object possesses a magnetic field or is expelling ionized gas, electromagnetic interactions between the object and the solar wind can occur. Could this generate a force? In theory, yes. In practical terms, the forces involved are minuscule unless the object possesses a remarkably strong magnetic field or is generating an immense volume of ionized gas. We have no evidence to suggest that 3I Atlas possesses a magnetic field, and the observed rate of ionized gas production is not extraordinary. Therefore, plasma interactions are unlikely to be the underlying cause. Fourthly, some form of exotic volatile. It is conceivable that the object contains ultra-volatile ices, substances that sublimate at extremely low temperatures and produce jets with exceptionally high velocities. Examples include hydrogen ice or helium ice. These would be largely undetectable by most instruments, as they do not fluoresce in optical wavelengths and do not generate dust. This would result in thrust without any visible debris. The inherent difficulty with this scenario lies in the extreme challenge of retaining such ices. They sublimate at temperatures infinitesimally close to absolute zero. Even within the frigid environment of interstellar space, within the coldest molecular clouds, retaining these ices for millions of years is problematic, and upon approaching any star, they would dissipate within mere seconds. Thus, while an imaginative hypothesis, it falters under rigorous examination. Fifthly, and this is where speculation enters, perhaps the object is utilizing a propulsion system beyond our current comprehension. Not a conventional rocket, nor outgassing as understood traditionally, but something entirely different. A sail adept at capturing solar wind with superior efficiency. A magnetic scoop that funnels charged particles and expels them for propulsion. A drive based on physics we have yet to discover. This falls into the category of we don't know what we don't know. It's unsatisfying due to the lack of a defined mechanism, but it is an honest acknowledgement of our current limitations. It signifies, given the observations and the absence of a fitting natural explanation, we must entertain the possibility that something novel is occurring. The subsequent investigations are designed to rigorously test these alternative hypotheses. If radiation pressure or thermal effects are indeed the drivers, the acceleration should continue in a predictable pattern. If outgassing is the cause, we ought to observe the associated debris cloud and be able to correlate the thrust with mass loss. If the phenomenon is of an exotic nature, we might detect signatures that are currently unexpected, such as radio emissions, magnetic field anomalies, or polarization variations. The collected data will serve to narrow down the possibilities. However, what if none of the natural mechanisms prove to be a suitable fit? What if we are left with an acceleration that defies explanation by established physics? This is the juncture where speculation becomes serious, where one is compelled to pose the question that, though unspoken by many, is present in everyone's minds. Could this be an intentional act? Part 10. Speculation and the possibility of intentional design. Hypothesis. This is the point where we venture beyond established observational evidence. Up to this juncture, every described element has been grounded in documented observations, measurements, and published research. While unconventional, these aspects are empirically verifiable. Now, we will delve into more speculative possibilities, ideas that lack definitive proof or confirmation but are suggested by the gathered data. If speculation makes you uncomfortable, I understand. Science is inherently conservative, cautious, and skeptical. However, science must also remain true to the evidence, and occasionally, the evidence points towards answers that seem to belong in the realm of fiction. Therefore, let us outline the decision-making framework. If the observations from November and December reveal a substantial debris cloud, if we detect approximately 5 billion tons of ejected material, then our inquiry will have reached its conclusion. 3I Atlas will be classified as a natural comet, an exceptionally extreme example, perhaps the most extraordinary ever encountered, but fundamentally natural. It will be understood to have formed in an unusual environment, possessing a unique composition, and exhibiting peculiar behavior due to its extrasolar origin, where established norms may differ. The mystery will be resolved. We will publish our findings, update our models, and move forward. Science will have triumphed. However, if the observations fail to indicate a debris cloud, if the acceleration persists without any discernible loss of mass, then we face a quandary that compels us to consider options we would prefer to avoid. Option 1. We are misinterpreting the measurements. The positional offset is indeed real, but it is not attributable to acceleration. Perhaps it is a parallax effect, a viewing geometry anomaly, or an as-yet unidentified instrumental artifact. This is the "we made an error" hypothesis. While potentially embarrassing, such occurrences are not unheard of. Science is a human endeavor, and humans are prone to mistakes. If this proves to be the explanation, we will eventually uncover it. Someone will identify the flaw in the coding or the systematic error in the calibration, and a collective sigh of relief will ensue. Option 2. There exists a natural mechanism that remains unknown to us. This could involve exotic physics, unusual chemical processes, or an interaction between the object and its environment that generates thrust without producing visible debris. It might be the venting of supervolatiles undetectable by our instruments, or an unconventional utilization of radiation pressure, or perhaps a novel force or effect that becomes significant only under specific conditions. This is the new physics hypothesis. It is intellectually stimulating, but necessitates an expansion of our theoretical frameworks. It implies rewriting textbooks and acknowledging that the universe is more complex than our current models adequately represent. Option 3. The object is artificial, deliberately designed, constructed, and dispatched with a specific purpose. This hypothesis elicits discomfort because it implies the existence of intelligence, advanced technology, and a confirmation that we are not alone, with beings possessing capabilities beyond our own. Let me be unequivocally clear. I am not asserting that option 3 is the definitive answer. I am stating that it is a possibility under consideration. It is consistent with the available data. And in the scientific realm, one cannot dismiss hypotheses simply because they are socially inconvenient. Let us explore the implications of option 3. If 3I Atlas is indeed a probe, a spacecraft, or an engineered artifact, then several aspects of its behavior would become comprehensible. Its trajectory would make logical sense. A deliberate path would be designed to include close passes by Mars and Venus for observational purposes and a close perihelion approach for solar study. Such a trajectory would maximize scientific return, mirroring our own exploratory missions. The timing of its arrival would also be rational, coinciding with favorable planetary alignments and potentially utilizing gravity assists for efficiency, optimizing either fuel consumption or travel time. Its composition would align with engineering principles. Constructing a probe from water ice would be impractical due to its reactivity, tendency to freeze and expand, and lack of long-term stability. Materials chosen for their ability to withstand temperature fluctuations and radiation would be preferred. Carbon dioxide ice emerges as a plausible propellant choice due to its stability at low temperatures and clean sublimation upon heating. Nickel alloys are standard materials in aerospace engineering. The observed low water content and unusual metal ratios are more consistent with manufactured origins than with natural formation processes. The observed acceleration would also be understandable. A perihelion passage would be an opportune moment to adjust trajectory, deploying thrusters or a sail, or activating whatever propulsion system is employed. Such maneuvers might be timed during solar conjunction when Earth-based observation is impossible, not for secrecy, but because the geometric configuration is optimal. The absence of a visible debris cloud would be explicable, as the propulsion would not be a random outgassing event, but a precisely directed thrust, utilizing only the necessary amount of propellant for the maneuver, thereby avoiding the wasteful creation of spectacular tails. The observed brightening and jets would also be coherent with this hypothesis. Brightness changes would be expected as systems are activated, and jets deviating from natural geometries would be consistent with controlled propulsion. Gas-dominated emission would be favored for its efficiency in generating thrust per unit mass, as opposed to dust. Every anomaly, every peculiar characteristic becomes explicable when assuming deliberate design rather than random natural processes. Now, it is crucial to understand that fitting a hypothesis to observed data does not automatically validate it. One can construct a narrative to explain virtually anything with sufficient creativity. The true test of a hypothesis lies not solely in its ability to align with observations, but in its capacity to generate predictions, the testability of those predictions, and the comparative improbability of alternative explanations. Therefore, what would be required to definitively confirm 3I Atlas as artificial? Firstly, we must exhaustively rule out all plausible natural explanations. This entails demonstrating unequivocally that no conceivable combination of exotic chemistry, unusual physics, or edge case conditions could account for the observed behavior. This is a formidable task, as nature is remarkably versatile, and one can always posit rare scenarios or improbable coincidences. However, if a sufficient number of natural explanations falter and the range of possible parameters becomes severely constrained, then the alternative hypothesis warrants serious consideration. Secondly, we would need unambiguous positive evidence of intelligent design. This might manifest as patterns exhibiting a regularity too precise to be natural, signals conveying information, structures demonstrating clear engineering principles, or modulations in brightness, or emissions suggestive of communication or control. Spectroscopic signatures of manufactured materials, such as industrial polymers or refined metals not found in nature, would also be compelling. None of these indicators have been definitively identified thus far, but the search continues. Thirdly, independent confirmation would be essential. A single anomalous object might be considered a fluke. Two objects exhibiting similar characteristics would suggest a pattern. Three such objects would elevate it to the status of a phenomenon. If 3I Atlas is indeed artificial, it is unlikely to be unique. Other similar entities should exist. Perhaps we have already encountered them without recognizing their nature. Oumuamua could have been one such object, or the next interstellar visitor might display analogous features. If we begin to identify additional objects possessing these characteristics, the artificial hypothesis gains substantial credibility. However, it is important to address the counter-arguments, as there are valid reasons for skepticism. Firstly, the overwhelming majority of the scientific community favors natural explanations. It's not because of a lack of open-mindedness or a fear of the consequences, but rather because natural phenomena possess a far more reliable history. Every single time humanity has encountered something perplexing throughout history, from celestial wanderings to pulsars to transient radio signals from space, the explanation has invariably been natural. Never once has an extraterrestrial intelligence been the answer. This established pattern creates a strong prior expectation, suggesting that before attributing phenomena to intelligent design, every other conceivable explanation must be thoroughly exhausted. Secondly, traversing the vast distances between stars is an undertaking of immense difficulty. The sheer scale of these distances is incomprehensible, and the timeframes involved span generations. The energy required for such journeys is staggering. Even traveling at a substantial fraction of the speed of light, crossing the void between stars would necessitate decades, if not centuries. And here, a crucial detail. Oumuamua, the object in question, is not traveling at such extraordinary velocities. Its speed is approximately 30 kilometers per second. While this is rapid by human standards, it is infinitesimally slow on an interstellar scale. At this pace, reaching the closest star would require tens of thousands of years. It begs the question, why would any civilization embark on sending a probe on a mission that outlasts the lifespan of most known civilizations? Why not await superior technology, opt for sending signals instead, or simply refrain from such an endeavor? Thirdly, if probes were indeed traversing our solar system, it is reasonable to assume we would have detected a greater number of them by now. For several decades, we have diligently observed the cosmos. We have catalogued hundreds of thousands of asteroids and comets, yet we have identified precisely 3 interstellar objects. If one of those were to be artificial, it would signify a detection rate of 33%. This figure seems exceptionally high. Unless probes are exceedingly common, unless the galaxy is teeming with them, the probability of us inadvertently stumbling upon one within the initial years of observation is infinitesimally small. These are valid points of contention, and they are the primary reasons why most scientists are hesitant to embrace the artificial hypothesis. However, they are not conclusive arguments. They are based on probabilities rather than concrete evidence, and occasionally improbable events do occur. The universe at times presents unexpected phenomena. The pertinent question then becomes, what threshold of evidence is required before an unlikely notion warrants serious consideration? Avi Loeb, the astronomer previously mentioned, has posited that we should at least explore the possibility. His stance is not that Oumuamua is definitively artificial. Rather, it is that we should refrain from dismissing the idea without rigorous examination. His argument advocates for the systematic collection of data, the testing of predictions, and allowing the evidence to guide our conclusions. If the object is eventually determined to be natural, then so be it. We will have gained valuable insights into exotic comets. But if it proves to be something else, and we neglect the clues simply because we are hesitant to confront the implications, then we have failed in our scientific duty, allowing our preconceptions to obscure potential discoveries. And here lies an uncomfortable truth. If probes from other civilizations are indeed traversing the galaxy, observing solar systems, and gathering data, it is plausible that they would resemble Oumuamua, small, swift, following unconventional trajectories, and exhibiting peculiar behavior near stars. We would not expect them to announce their presence or to land on Earth and introduce themselves. Instead, we would anticipate them to behave precisely as our own probes do: observe, measure, and continue on their journey. And should we encounter one, it is highly probable that we would engage in debates for years, as the evidence would be compelling, yet not definitive, sufficiently ambiguous to allow skeptics to maintain their skepticism and proponents to remain intrigued. This is the current state of affairs, the prevailing situation. The 10th anomaly, the unexplained acceleration unaccompanied by debris, is the pivotal element. If this observation holds true, and if December brings no evidence of a debris cloud, then the artificial hypothesis will transition from the realm of fringe speculation to that of serious scientific consideration. This does not imply certainty or proof, but rather a hypothesis that demands our attention. And for those who believe that the search for extraterrestrial intelligence is a worthwhile pursuit, who deem it important to ascertain whether humanity is alone in the cosmos, then this particular object currently represents one of the most significant targets of our scientific endeavors. Therefore, let us broaden our perspective. Let us connect this narrative to the wider context of recent astronomical discoveries and consider what else has transpired in the year 2025 that positions Oumuamua as part of a larger cosmic pattern. Part 11. Recent Astronomy News. 1. Exoplanet Atmosphere Surprise. While our attention has been captivated by an interstellar visitor within our immediate celestial neighborhood, astronomers studying distant star systems have also been encountering their own unexpected findings. In September 2025, a research team utilizing the James Webb Space Telescope announced the detection of an exoplanet atmosphere that defies all current predictive models. The planet, designated WASP 243b, orbits a star similar to our Sun, located approximately 400 light-years away. It is classified as a hot Jupiter, a gas giant that orbits its star at a very close distance, resulting in tidal locking where one hemisphere perpetually faces the intense stellar heat. Standard theoretical models predict that such atmospheres should be predominantly composed of hydrogen and helium, with trace amounts of water, carbon monoxide, and possibly methane or ammonia. However, the atmosphere of WASP 243b is dominated by carbon dioxide, constituting nearly 50% of its volume. The presence of water is negligible, and while hydrogen and helium are present, they are not the primary constituents. The observed spectrum reveals molecular signatures that do not align with any known solar system atmosphere or any theoretical framework for the formation of hot Jupiters. It is as if this planet condensed in an environment where carbon was significantly more abundant than oxygen, or where some unknown process selectively removed hydrogen and concentrated carbon dioxide. In either scenario, the findings contradict established understanding. Such an atmosphere should not exist. The research team published their findings in the journal Nature, eliciting a mixed reaction of excitement and perplexity within the exoplanet research community. Excitement stemmed from the acquisition of a novel data point, revealing a new class of celestial body that expands our comprehension of planetary diversity. Confusion arose because no one could readily explain the formation of such an atmosphere. The leading hypothesis suggests that the planet originated farther from its star, in a region rich in carbon dioxide ice, and subsequently migrated inward. However, this explanation does not fully account for the extreme atmospheric composition, nor does it clarify why hydrogen and helium, being the most prevalent elements in the universe, did not become the dominant atmospheric components. So, what is the connection between this discovery and Oumuamua? On the surface, seemingly none. One is an interstellar object within our solar system, while the other is an exoplanet atmosphere located hundreds of light-years away. Yet, thematically, they are linked. Both represent instances of the universe generating phenomena that deviate from our established models. Both are outliers that challenge our fundamental assumptions regarding composition and formation processes. Both are compelling astronomers to confront the disquieting possibility that our current theories are incomplete. For decades, our models of planetary formation have been constructed based on observations of our own solar system, proceeding under the assumption that our solar system is typical and that other planetary systems would exhibit similar characteristics with minor variations. However, with each new exoplanet discovery, it becomes increasingly apparent how exceptional our own solar system might be. Early theoretical models suggested that hot Jupiters should not exist. Similarly, super-Earths in tight orbits, ice giants with retrograde orbits, and now atmospheres dominated by carbon dioxide were all deemed improbable. Yet they all exist. The overarching lesson is one of humility. The universe is under no obligation to conform to our preconceived notions. Planetary formation processes are inherently complex, environments are incredibly diverse, and edge cases appear to be far more common than initially anticipated. When one considers the vast number of star systems, each possessing its unique history and chemical composition, the range of possibilities becomes immense. Some regions of this vast parameter space yield outcomes familiar to us. Other regions produce results that appear strange to us, but are entirely natural given the prevailing conditions. Therefore, when we examine Oumuamua and observe its unusual composition, scratching our heads in bewilderment, Perhaps we should not be surprised. It is conceivable that objects of this nature are prevalent in specific stellar environments, the very same environments that give rise to peculiar exoplanet atmospheres. Perhaps the simultaneous discovery of an anomalous interstellar object and an anomalous exoplanet atmosphere in the same year is not a mere coincidence, but a discernible signal indicating that the cosmos possesses more hidden complexities than we have hitherto accounted for. This realization does not confirm that Oumuamua is natural, nor does it definitively prove anything in either direction. However, it provides crucial context. It serves as a reminder that strangeness is increasingly becoming the norm in astronomical observations. Every new instrument, every new survey is revealing phenomena that deviate from established textbooks. Consequently, our astonishment at Oumuamua's peculiar characteristics should perhaps be tempered by the acknowledgement that the universe is replete with surprises. Some of these surprises are natural, while others may not be. The only reliable method to ascertain the truth is to persist in observation, measurement, and rigorous testing. Speaking of testing, another scientific frontier has witnessed significant advancements in 2025, namely the realm of fundamental physics, where scientists are employing the cosmos itself as a vast laboratory to probe the limitations of our theoretical frameworks. Part 12. Recent Physics News. Tests of General Relativity, Gravitational Lensing Advances. In March 2025, a team of physicists published findings from a solar lensing experiment that achieved an unprecedented level of precision. By utilizing a network of telescopes strategically positioned across Earth, they meticulously measured the deflection of starlight as it passed near the Sun during a partial solar eclipse. The fundamental technique employed is identical to that used in 1919 to validate Einstein's theory of general relativity. However, with the sophisticated instrumentation and advanced data analysis methods available today, the precision of these measurements is thousands of times greater. The outcome of this experiment confirms that general relativity remains accurate to within 1 part in 10 million. The measured deflection precisely matches Einstein's predictions, exhibiting no deviations, no anomalies, and no indications of modified gravity, extra dimensions, or any of the other exotic alternative theories that theorists have proposed over the years. The Sun bends spacetime exactly as predicted. The universe, at least within this specific region and under these particular conditions, adheres to its established laws. This might sound like a mundane confirmation of a long-held belief. However, the implications are profound. Every test of general relativity represents an opportunity for the theory to be falsified. Each measurement serves as a potential fissure in its theoretical foundation. The persistent validation of general relativity, decade after decade, with ever-increasing precision, strongly suggests that whatever the ultimate theory of quantum gravity may be, it must ultimately reduce to general relativity in the classical limit. Einstein profoundly grasped a fundamental aspect of the nature of spacetime. Now, let's consider how this connects to Oumuamua. An early analysis of the object's trajectory indicated that gravitational lensing by the Sun should induce a small yet measurable shift in its apparent position. The formula for this effect is straightforward. The deflection angle is directly proportional to the gravitational constant, the mass of the Sun, the speed of light squared, and inversely proportional to the impact parameter's geometry. For Oumuamua, at its closest approach to the Sun, the predicted lensing deflection is approximately 0.2727 arc-seconds per degree of angular separation from the Sun's center. While this is a small value, it is not zero. Crucially, it is significantly less than the observed 4 arc-second offset, meaning that gravitational lensing cannot account for the positional anomaly. The offset is genuine and attributable to a factor other than the curvature of spacetime near the Sun. This could be due to non-gravitational acceleration, a measurement error, or an as-yet unidentified phenomenon, but not lensing. This finding is significant as it eliminates one potential explanation, thereby narrowing the field of possibilities. Furthermore, it provides a test case for physics. If Oumuamua's motion is indeed anomalous, if the acceleration is real, then we are presented with a rare opportunity to examine physics using an object originating from beyond our solar system. We can assess how gravity influences an object from outside our solar system. We can verify whether the gravitational constant remains consistent for interstellar matter compared to matter within our solar system. We can search for minute deviations that might hint at new physical principles. To date, no such deviations have been observed. The gravitational deflection precisely matches theoretical predictions. The object's orbit adheres to Newtonian mechanics, augmented by relativistic corrections, exactly as expected, with the exception of the non-gravitational component. This implies that whatever is causing the acceleration, it does not stem from a breakdown in the principles of gravity itself. Rather, it suggests an alternative cause. This leads to an interesting philosophical consideration. We inhabit a universe governed by laws. As far as we can ascertain, these laws are universal, operating consistently across all regions of space and time. Gravity on Earth is identical to gravity in the vicinity of a distant quasar. The speed of light remains constant, irrespective of whether one is within a laboratory setting or traversing intergalactic space. This universality is a foundational principle of physics, enabling us to make predictions and to confidently guide spacecraft to other planets, knowing they will arrive at their calculated destinations. But what if these laws are not universally applicable? What if there are specific regions of space, particular types of matter, or unique conditions under which the rules are altered? What if interstellar objects originating from certain environments behave differently due to having formed under distinct physical regimes? Such notions may sound like fantasy, yet they are empirically testable. The approach involves comparing objects from different origins and observing whether they conform to the same mathematical equations. Thus far, they have. Oumuamua, despite its numerous peculiarities, continues to obey the laws of gravity and the principle of conservation of momentum, at least in the sense that if it is accelerating, a force must be acting upon it. The fundamental question remains: what is the source of this force? The observations scheduled for December are anticipated to provide an answer. We may either witness the presence of a debris cloud, confirming outgassing as the operative mechanism, or we may not, compelling us to consider less conventional explanations. However, regardless of the outcome, the findings will be constrained by our current understanding of physical laws, unless those laws themselves prove to be incomplete, which in itself would be an even more astonishing revelation than discovering an alien probe. Let us now shift our focus to human technological advancements. While we are actively investigating interstellar visitors, we are also in the process of becoming an interstellar civilization ourselves. The parallels are remarkably striking. Part 13. Recent Space Technology News. Commercial Spacecraft, Solar Skimmers, and Sail Propulsion. In August 2025, a private aerospace company named Heliodine achieved a significant milestone by successfully demonstrating a solar sail spacecraft capable of skimming within 10 million kilometers of the Sun. The mission, codenamed Project Icarus II, employed a reflective sail measuring 50 meters in diameter to harness the pressure exerted by solar radiation. As the spacecraft approached the Sun, the intensity of sunlight increased, allowing the sail to capture momentum and accelerate the probe to speeds exceeding 100 kilometers per second. This velocity represents a substantial fraction of the escape velocity from the solar system. The primary objective of this mission was to evaluate propulsion concepts for future interstellar probes. The underlying principle is elegantly simple: utilize the Sun as a launch pad. Approach closely, deploy the sail, capture the intense solar radiation, and execute an outward slingshot maneuver. This method eschews rockets and conventional fuel, relying solely on photons and the principles of physics. It is both elegant and efficient, and demonstrably effective. Project Icarus II is now on a trajectory that will carry it out of the solar system entirely, marking it as humanity's fifth interstellar object, following in the footsteps of Voyager 1, Voyager 2, Pioneer 10, and New Horizons. This mission generated considerable enthusiasm within the space exploration community. It unequivocally proved the viability of solar sails for deep space exploration. It demonstrated the capability to achieve high velocities without the encumbrance of carrying substantial propellant mass. Furthermore, it paved the way for serious discussions regarding the feasibility of sending probes to nearby star systems within a human lifetime. This does not pertain to interstellar colonization or crewed missions, but rather to the deployment of small, fast probes that could reach neighboring stars in decades rather than millennia. Now, consider the implications of this development in the context of Oumuamua. We are actively developing technology to dispatch objects on trajectories that involve close solar approaches, thereby gaining velocity and venturing into interstellar space. From the perspective of an external observer, these objects would bear a striking resemblance to comets. They would approach the Sun, brighten due to reflected sunlight, and experience acceleration near their perihelion due to the deployment of sails or the activation of jet thrusters. If one were unaware of their artificial origin and simply observed them as faint bodies on hyperbolic trajectories, they might be classified as unusual comets. The analogy is not perfect. Project Icarus II consists of a thin sail, not a solid mass, and it lacks the nucleus, coma, or other features typically associated with comets. However, conceptually, the parallels are strong. It is an object that leverages solar energy to alter its trajectory, and if humanity, with its current technological limitations and resources, is capable of achieving this in 2025, imagine the capabilities of a civilization far more advanced. What might their probes look like? Perhaps they would employ a hybrid approach, combining sail technology with outgassing mechanisms. They might carry propellants like carbon dioxide ice, which could serve a dual purpose as a heat sink and a thruster fuel. It is conceivable they would coat their probes with materials that reflect light in unusual ways, generating polarization signatures that deviate from those of natural objects. They might design trajectories optimized for close encounters with scientifically interesting planets, utilizing gravity assists and precisely calculated thruster firings. In essence, they might construct something that closely resembles Oumuamua. This does not constitute proof, but it effectively demonstrates that the artificial hypothesis is not inherently absurd. It does not necessitate the invocation of magic or impossible physics. Rather, it relies on technological capabilities that are merely a few steps beyond our current achievements. And if humanity has reached this level of sophistication within a few thousand years of civilization, consider the advancements achievable by a civilization a million years our senior. The disparity between our current capabilities and theirs would be far greater than the gap between ourselves and microorganisms. Their probes could be so advanced, so meticulously engineered, that they would be virtually indistinguishable from natural objects, save for minor anomalies such as excessive acceleration, unusual composition, or trajectories that appear suspiciously convenient. Project Icarus II also underscores a critical point. Solar skimming maneuvers have transitioned from the realm of science fiction to that of practical engineering. Consequently, when we observe an object executing such a maneuver, we cannot automatically assume its natural origin simply because its behavior aligns with phenomena we associate with comets. Comets release gas near the Sun, and solar sails accelerate in its vicinity, both producing similar observable effects. Differentiating between them requires meticulous analysis of specific details, and at times, these details can be ambiguous. Therefore, we observe, we measure, and we await the observations planned for December. And while we wait, we continue to refine our own technology, pushing the boundaries of our capabilities, actively striving to become the very type of civilization that might one day dispatch probes to distant stars. The irony is palpable. We are simultaneously searching for evidence of extraterrestrial intelligence and becoming evidence of intelligence ourselves. If there are beings out there observing us with the same scrutiny that we apply to Oumuamua, they are likely engaged in similar debates. Is it natural? Is it artificial? Should we pursue further investigation? Or should we simply categorize it as another peculiarity in a universe already replete with anomalies? Let us now examine one final piece of recent technological news as it directly relates to our methods of monitoring objects like Oumuamua and its implications for the future. Part 14. Recent AI Computation News. 4. AI-assisted asteroid and comet monitoring and anomaly detection. In June 2025, the European Space Agency implemented an artificial intelligence system named Sentinel AI, tasked with monitoring small bodies within the solar system. This system employs machine learning algorithms that have been trained on decades of observational data pertaining to asteroids and comets, enabling it to identify anomalies in real time. When a survey telescope detects a new celestial object, Sentinel AI proceeds to analyze its orbit, brightness, spectral characteristics, and morphology. It then compares these properties against established databases of known objects. If any characteristics are found to be anomalous or unexpected, the system flags the object for human review and automatically initiates follow-up observations. The system has already demonstrated its considerable value. In its initial 3 months of operation, Sentinel AI identified 17 objects exhibiting anomalous properties that might have been overlooked by traditional analytical methods. While the majority of these were subsequently identified as misclassifications or instrumental artifacts, 2 were genuine discoveries, representing significant additions to our astronomical knowledge. A celestial wanderer from the main asteroid belt, exhibiting an exceptionally high output of carbon monoxide, and a near-Earth asteroid with a rotational speed so astonishingly rapid that centrifugal forces should be actively disintegrating it, yet it inexplicably remains intact. The overarching implication is our entry into an epoch where the identification of anomalies is becoming an automated process. We are no longer dependent on human observation to pinpoint the unusual. Instead, we are instructing machines to perform this crucial task. Machines excel in this domain because they are unburdened by preconceived notions or biases, not expecting phenomena to conform to a specific appearance. They meticulously compare incoming data against established models and flag any discrepancies. Should an object demonstrate acceleration beyond what is anticipated, the algorithm detects it. If its elemental composition deviates from the norm, the algorithm flags it. In the event of an improbable trajectory, the algorithm registers it. Now, let us consider this applied to the object designated 3I Atlas. This celestial body was initially detected by a conventional survey system in Chile, but a multitude of its peculiar characteristics were subsequently identified by automated analytical frameworks. Its highly unusual orbital path was recognized instantaneously once software processed its trajectory and determined it to be hyperbolic. Anomalies in its composition were brought to light when spectroscopic analysis pipelines cross-referenced the gathered data with standard comet profiles, revealing significant deviations. A notable surge in its brightness was captured because photometric monitoring systems observed a departure from the predictable light intensity pattern. None of these discoveries necessitated a human observer at a telescope proclaiming, "That's peculiar." The machine identified it first. This represents the vanguard of research into small celestial bodies. Expansive observation projects, such as the soon-to-be operational Vera C. Rubin Observatory, are projected to catalog millions of cosmic entities. The sheer volume of this data renders human analysis infeasible. We require artificial intelligence, systems capable of sifting through vast data sets, isolating the outliers, and prioritizing them for subsequent, more detailed investigation. As these intelligent systems evolve and refine their ability to discern patterns and anomalies, we will undoubtedly encounter more objects akin to Three-Eye Atlas, perhaps even in greater numbers. This prompts a critical question. Is Three-Eye Atlas a singular phenomenon, or is it merely the vanguard of numerous interstellar voyagers that we are now equipped to detect with our advanced instrumentation? The three confirmed interstellar objects thus far identified, Oumuamua, Borisov, and Three-Eye Atlas, have all been discovered within the last 8 years, indicating an approximate discovery rate of one object every 3 years. However, detection rates are intrinsically linked to the sensitivity of observational surveys. As our telescopes become more powerful and our analytical algorithms more sophisticated, our capacity to detect fainter, more distant objects and those on less conventional trajectories will expand. The actual number of interstellar visitors traversing our solar system at any given moment could range from hundreds to thousands. We are only now developing the capabilities necessary to perceive them. Furthermore, if even a modest fraction of these transient visitors exhibit characteristics comparable to Three-Eye Atlas, if a mere 1% are found to be of artificial origin or behave in ways defying our current understanding of natural physics, then we are witnessing a fundamental paradigm shift. We are transitioning from a cosmos where interstellar objects are infrequent curiosities to one where they are sufficiently abundant for systematic scientific study. In such a redefined universe, the age-old question, "Are we alone?" becomes amenable to an answer, not through the reception of radio signals or the identification of megastructures, but through the observed behavior of small bodies journeying through our celestial neighborhood. Sentinel AI and analogous systems serve as the perceptive organs of this new era, diligently monitoring for the 11th, 12th, and even the 100th such object. They are systematically compiling databases of their properties, seeking correlations, rigorously testing hypotheses, and ensuring that when the next Three-Eye Atlas emerges, we will be fully prepared. We will have established protocols, aligned instruments, and pre-formulated inquiries ready. The universe is no longer a passive entity for us to merely observe. It has become an active domain we interrogate, and it is responding to our inquiries, one anomalous object at a time. So, what is our current position? What phenomena should we be scrutinizing? What are the ultimate significations of these discoveries? Part 15. Conclusion. Future observational targets and broader implications. As I am recording this in November of the year 2025, December is rapidly approaching. The closest perihelion passage of Three-Eye Atlas will occur on December 19th. In the ensuing weeks, telescopes across the globe will be focused on a specific sector of the sky within the constellation Pisces in pursuit of a faint, swiftly moving object potentially accompanied by a debris trail. Here is what we will be meticulously examining. Firstly, the object's morphology. Does it possess a discernible tail? Has its coma expanded significantly since its closest approach to the Sun? Are there any structural indicators suggestive of substantial material ejection? These features will be discernible in optical and infrared imaging. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories equipped with adaptive optics will all be capturing high-resolution imagery. If a debris cloud is present, it will manifest as a diffuse luminescence, possibly exhibiting streamers, jets, or fragmented components. The observed morphology will provide insights into whether the outgassing was uniform or localized and whether the object is intact or undergoing fragmentation. Secondly, photometry. Has its brightness undergone variations consistent with a comet expelling billions of tons of material? We are specifically seeking characteristic signatures such as a brightening that correlates with its solar distance, color shifts indicative of dust or gas emission, and fluctuations that might suggest rotation or the presence of active surface regions. If substantial mass loss has indeed occurred, photometric data will corroborate this. Conversely, if it has not, its light curve will appear flat or display patterns incongruent with conventional cometary models. Thirdly, spectroscopy. What molecular constituents are present within its coma? Are we detecting expected volatile compounds such as water, carbon dioxide, carbon monoxide, or cyanide? Are there any unanticipated species, perhaps industrial chemicals or synthetic compounds? Do the observed ratios align with typical natural outgassing processes, or do they suggest a more controlled emission mechanism? Spectroscopy stands as one of our most potent diagnostic instruments, capable of elucidating not only the elemental composition, but also the relative abundances and their plausibility in conjunction with other observational data. Fourthly, astrometry. Precisely where is the object located, and does its position align with predictions derived from gravitational models, accounting for any inferred non-gravitational accelerations? If the observed acceleration persists and the trajectory continues to deviate in a consistent manner, it strengthens the assertion that a genuine phenomenon is at play. If its current position matches predictions, it may indicate that the earlier deviation was an anomaly or that the acceleration was transient and has since ceased. In either case, astrometric data will serve to delineate the range of possible explanations. Fifthly, radio observations. Is there any detectable emission in the radio spectrum? Natural comets do not typically generate strong radio signals, although certain types of plasma interactions or magnetic fields could potentially do so. Artificial objects, on the other hand, might produce radio noise originating from their internal electronics or power systems. While this is a less probable scenario, it warrants thorough investigation. Facilities such as the Atacama Large Millimeter, Submillimeter Array, ALMA, and the Very Large Array, VLA, will be actively engaged in listening for such emissions. If there is anything to detect, these instruments will likely succeed. Sixthly, polarimetry. Are there any observable alterations in its polarization signature? Has the negative polarization persisted, or has it evolved as the object recedes from the Sun? Polarization is highly sensitive to particle size and composition. Consequently, any observed changes could signify the exposure of fresh material or the ongoing evolution of cometary particles within the coma. These, then, are the observable phenomena, the events, or lack thereof, that we anticipate over the next month. Depending on our findings, we will likely arrive at one of three distinct conclusions. Scenario A. The presence of a debris cloud is confirmed. This cloud is massive, luminous, and consistent with the ejection of approximately 5 billion tons of material. The observed acceleration is fully attributable to outgassing processes. 3I Atlas would then be classified as the most extreme interstellar comet ever documented, serving as a critical benchmark for future research and a stark reminder that the universe, while perhaps stranger than we initially conceived, fundamentally operates according to natural laws. This represents the most conservative outcome, aligning with the expectations of the majority of the scientific community. It implies a significant expansion of our understanding of cometary diversity without necessitating a radical revision of existing scientific literature. Numerous academic papers will be published, models will be refined, and in a few years, 3I Atlas will likely be relegated to a footnote in the annals of planetary science. An interesting one, perhaps, but not a groundbreaking one. Scenario B. No discernible debris cloud is detected. The observed acceleration is validated, yet there is no visible evidence of mass expulsion. The observations indicate activity, but not to the magnitude required to explain the acceleration. This suggests either an error in our estimations of the object's mass, a misunderstanding of its ejection velocity, or that the object possesses fundamentally unique characteristics. This outcome presents a significant intellectual challenge, compelling us to consider the possibility that either our current understanding of physics is incomplete or the object employs an unknown mechanism. It could be natural, exotic, or even artificial, but it definitively deviates from the characteristics of a conventional comet. This scenario inevitably opens the door to speculation, intense debate, and considerable controversy. Some researchers will champion the pursuit of new physical principles, while others will meticulously re-examine the data for potential errors. A select, albeit growing minority, may propose that the hypothesis of artificial origin warrants serious consideration not as a definitive conclusion, but as a plausible avenue for further investigation. Scenario C. Partial debris detection with an incomplete explanation. It is possible that we may observe some evidence of mass loss, but not to the extent anticipated. Alternatively, photometric data might indicate a brightening, but its pattern could prove inconsistent with expected phenomena. Spectroscopy might reveal unusual molecules that do not conform to established models. This represents an ambiguous outcome, inherently unsatisfying as it fails to provide definitive resolution, but rather generates further questions. Nevertheless, it is arguably the most probable scenario, given that reality is often intricate and nature seldom provides simple answers. Should this be the eventual conclusion, the debate will undoubtedly persist. Additional observational time will be sought, more research papers will be authored, and 3I Atlas will remain an enigma, at least for an extended period. Irrespective of the scenario ultimately realized, the implications are profound. For the field of interstellar object research, we are learning that the vast expanse between stars is not a void. It is populated by objects exhibiting compositions and behaviors that reflect their diverse origins. Some may be pristine remnants from the formation of planetary systems. Others could be fragments resulting from collisions or ejections, and a small subset might represent something entirely different. Comprehending this population and characterizing their unique properties constitutes a significant frontier in astronomical inquiry. Each newly identified interstellar visitor represents a valuable offering, a sample from another star system delivered at no cost. Our role is to examine these samples with sufficient diligence to unlock their secrets. From the perspective of planetary defense, objects exhibiting unexpected accelerations pose a significant concern. Our current tracking systems are predicated on the assumption that once an object's orbit is determined, its future trajectory can be predicted with high accuracy. However, if non-gravitational forces play a substantial role, and if celestial bodies can alter their course in ways we do not anticipate, then predictive capabilities become considerably more challenging. This does not imply an imminent celestial catastrophe, but rather a pressing need for enhanced models, more robust monitoring systems, and more comprehensive contingency strategies. We must acknowledge and account for inherent uncertainties and maintain a humble appreciation for the vast scope of our ignorance. For the search for extraterrestrial intelligence, SETI, objects like 3I Atlas present a novel avenue of investigation. It is conceivable that the technological signatures we are actively seeking are not confined to radio broadcasts or colossal megastructures. Perhaps they manifest as subtle anomalies in the orbital mechanics of small celestial bodies or as unexpected compositional anomalies within interstellar visitors.